All right, let's take a look at a geometric series and all the properties that kind of go with it. So a geometric series is defined by an infinite series that has this form: AR squared, AR cubed, plus dot 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 dot, AR to the n. Okay, so the first thing you want to notice is that the first term of the geometric series is always A, and then the geometric series is formed by this multiplier, so R is what you get multiplied by every single time to get a new term. Okay, and so let's think about what does this mean for the series. So we want to see if the series converges or not, or diverges. So pretty easy if you think about it. Converges if what? Well, if R is bigger than 1, you see how this series would actually grow? Because you're multiplying by something bigger than 1, you're going to get bigger and bigger and bigger and bigger, and if you keep getting bigger and bigger and bigger, and you add up an infinite number of those terms, well, it would seem like you'd have a bigger and bigger something. So it's actually going to converge only if R is strictly between -1 and 1, and it's going to diverge. Well, really, this diverges otherwise. Right, so if R is bigger than 1, equal to 1, equal to -1, or even -2, it happens. So what happens if it does converge? Well, what does it converge to? Well, we can look it up. We can prove it later, but we can show that if it converges, so if R is between -1 and 1, we can say that the sum of a geometric series is A over 1 minus R. Okay? And so we can look at some examples of this. Again, this is only true if it converges. It converges only if our R value is between -1 and 1. It doesn't depend on A at all in terms of whether it converges or not. The sum depends on A, but whether it converges or not is only dependent on R. And if it diverges, well then, remember, diverges means it has an infinite sum, or just alternates between some value, right? Right. So let's look at some examples. So first example, let's just go with some easy ones. So like, what if the series was 2 plus 1 plus a half plus a fourth plus dot 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 dot, and we keep going. What sum does that have? Okay, I think we can make an argument that that sum maybe is 2, and then it's 3, and then it's 3.5, and it's 3.75. Maybe the sum is going to go to 4, and we can show that that's actually correct. So what we need to establish is, what is A? A is equal to 2, and what's R? Well, R is a half. You see how this is A, and this is AR, and this is AR squared, and this is AR cubed. Again, you can kind of go through all of those things, but once you know that, and you know R fits this restriction, then you know the sum has to equal A over 1 minus R, and you get 2 over a half, which is 4, and you get that sum that we want. Okay, what if we looked at the series 9 minus 3 plus 1 minus a third plus dot 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 dot, right? Is that geometric? And you're like, well, the R here is -1/3. Now, what does a negative R value do? Well, it turns out that a negative R makes the series alternate. Because if you look at it, each one of these odd ones, AR, AR cubed, AR to the 5th, will have an odd number of R's, an odd number of negatives will make a negative, where an even number, R squared, no R, R to the 4th, well, those will still be positive, and so my series will go plus, minus, plus, minus, plus, minus. So, question, does it always go plus, minus, plus, minus? Could it go minus, plus, minus, plus? What would happen? Well, think about, what if A was negative? If A is negative, then the first term is negative. So a negative A and a negative R, well then it's going to be negative, 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 so positive. And so a negative A and a negative R are actually going to make it minus, plus, minus, plus. What if it was a negative a and a positive r? Well, if r is positive, then it doesn't alternate, and if a is negative, then all of these would just be negative. It'd be like taking this, make a negative 2, r a half, okay? If a is negative 2 and r is a positive a half, then we get this exact same series. They're just all negative. And so the sum would still be just a over 1 minus r, and of course you get negative 4, which would make sense because you have the addition of all these negative terms, which is like that. So we can have negative a values, we can have negative r values, again negative r values make it alternate. Negative a values just happen that the first term is negative. That's the only thing it controls. Okay, so let's take a look at this one. We get an a value of 9, and an r value, it's alternating, so it's going to be negative, and then what happens to 9? You multiply it by 1/3 to get it to that. So what's the sum? Well, the sum, because it does converge, because our r value is between our limit there, our restriction, is a over 1 minus r. Now remember, r is a negative 1/3, so this is going to be 9 over 4/3, which is 27/4, which may not have been something we would have just guessed. You know, this one was, I think, pretty easy to see that it was 4. We wouldn't have gotten 27/4 by just looking at it, but that's okay. We don't have to just look at everything and know. But again, a geometric series, so one, it always has this exact same pattern. If it doesn't have this pattern, if it doesn't go up or down by some multiple of r, up only if r is bigger than 1. Now again, it could be a geometric series, it just wouldn't be a convergent geometric series, it would diverge. But if it converges, r is like a half, negative 1/3, 1/4, 2/3, whatever, 4/5, then it converges, and it has to have this pattern. If it doesn't have this pattern, and if r isn't between negative 1 and 1, then it doesn't have this sum. Okay? So how else can we write this? Well, we can write this in a variety of ways. We can use just the notation I have been using, just the actual, I'm giving you the series, or I could give you something that looks like this. Okay? 0 to infinity of 4 to the 3/4 to the n. Again, what is that? Well, is it geometric? Well, remember, a geometric series has to always, always, always look like this. Every single time. But that, in sigma notation, is just summing up a r to the n when n equals 0 to infinity. And again, think about it. This term corresponds to n equals to 0. This is n equals to 1, n equals to 2, and so on. So this geometric series is the same thing as this. And we know as long as r is between negative 1 and 1, then this does have the sum equal to a over 1 minus r. Okay? So in this particular case, we can look at it, and again, there's no really tricks here. If n equals 0, then the first term is just 4. So we know that a is equal to 4. Clearly, when I keep letting n go up and up and up and up, n goes from 0 to 1 to 2, I'm getting one more factor of 3/4. So you easily can tell that our value is 3/4. Thus, the total sum is a over 1 minus r. 4 divided by 1/4 is, in fact, 16. Okay, so you get 16 in that case. So far, so good? Okay, so how can I make this more difficult? Okay, how about this one? What if I said this is n equals to 1 to infinity of 9 to the 2/3 to the n. So it looks like this is a and this is r, but this is a little trick. This is n equals to 1. So if you think about it, what is your first term? Well, the first term in the sequence is when n equals to 1. So what happens when n equals to 1? Well, when n equals to 1, this produces n equals to 1 produces a 2/3 times 9, which is 6. So n equals to 1 is the first term. So our a value is not 9, our a value is 6. N equals to 2, then I'm getting 2/3, another 2/3, which is just 2/3 of this. 2/3 of that is just 4, and dot, 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 and so on and so forth. Okay? So what you can tell is that a is no longer 9. A is actually 6. Now r is still 2/3, because we keep just getting another factor of 2/3. And so then our sum is a over 1 minus r. This is 6 over 1/3, which is 18. So that's a trick they can do. They can do another very similar thing. They can start it at n equals to 0. They could make this like 4 to the 3/4 n plus 1. Okay? And again, you can't just easily read off then, this isn't a r to the n. It's not the standard. If it's the standard, like this one, then you know that's a and that's r, and boom, you're kind of done. If they shift it here, you got to do a little work to figure out what a is, and if they shift it here, again, n equals to 0 is our first term, but when you plug in n equals to 0, you get 4 times 3/4 when you get 3. So 3 is actually our first term. And then after that, when n equals to 1, then you get 3/4 of that, and you get, oh, I guess that next term would be 9/4 plus dot, 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 dot. And again, certainly when you let n go from 0 to 1 to 2 to 3, you just keep getting another 3/4 and another 3/4 and another 3/4. So the hard part was figuring out that a was 3. Hopefully it's pretty clear that r is still 3/4. Shifting this is still going to be 2/3. You're still getting another 2/3 every time. And here you're still getting another 3/4 every time. So our sum then, this total summation is a over 1 minus r. This is 1/4, 3 over 1/4 is 12 in this case. Again, you can play little tricks here, you can shift it up here, you can shift it down here. You could have shifted both of those things. You got to make sure you actually find a. A is the first term, and the first term corresponds to the first n value. I mean, I can make n whatever I want. I can make it start at 3 if I wanted to. Then the first term would correspond to that particular n value. It doesn't happen much. Most of the time it is 0, but I could let this be n equals to 3 to infinity of 16 times 1/2 to the n. Again, my first term corresponds to n equals to 3. When n equals to 3, this is 1/8. 16 times 1/8 is 2. So my first term in this sequence is 2. And then after that, I keep getting another half, because when n equals to 4, I get 1 and dot, dot, dot. So I can see a is 2, r is still 1/2, and then I can get the sum. And in this case, the sum would equal to 4. So I can make this whatever I want. The first term in the sequence is always a, and then the multiplier is r. Right? This is a, and this is AR, and you can see here that a is 2, and then r must be 1/2. Okay, how else can they trick you for geometric? Well, they could give you something that looks like 2 to the n plus 3 to the n all over 4 to the n, and maybe they can do even 5 times 4 to the n. And they're just tricking you. This will just end up being the sum of 2 different geometric series. So this is the sum of 1/5 times 2/4 to the n plus the sum of 1/5 of 3/4 to the n. I guess let's make it 0 to infinity. And again, think of that algebra there, but that's not really too bad. This is just 2 fractions. And this 1/5 is with both of them. Right? This is just over 5. This 5 is not part of the n, so it's just chilling out as a 1/5. This is 2n over 4n, which is just 2/4 n. This is 3n over 4n, which is 3/4 n. And now each of these are their own geometric series. This is an a value of a fifth and an r value of 1/2. And this is an a value of a fifth and an r value of a third. So you do this sum plus this sum, and then you actually got it. So they can give you something funky that looks like this, but it's really not anything anything spectacular. You know, you could do 2 times 3 to the n minus 5 to the n all over 7 to the n, right? And that's just summing up 2 times 3/7 to the n minus the sum of 5/7 to the n. Okay, this would have an a value of 2 and an r value of 3/7, and then you'd subtract whatever this is, but this over here has an a value of 1 and an r value of 5/7, right? No big deal at all. Okay, so you can kind of think about how you do some of these adjustments, but again, a geometric series always has this exact form eventually. And we can start it at different n values, but it has this form because this equals a plus ar plus ar squared plus dot dot dot, and they call it the general term ar to the n. Okay, hopefully this gives you a good start on geometric series, finding their sum, deciding whether they converge or whether they diverge, looking at sigma notation versus an infinite sum of things. And again, we use the word sum because with geometric series, we're just talking about these are just numbers, and we're just adding up a bunch of numbers and deciding, well, do they have an infinite sum or a finite sum? And if they have a finite sum, and we do know whether they do or they don't. Again, we know they have a finite sum if this is true, strictly between -1 and 1. R cannot be 1. If R was equal to 1, this would just be a plus a plus a plus a plus a plus a, and we get an infinite number of a's, and an infinite number of a's, even if a is small, is still an infinite amount of things. Okay, so we do need R to be strictly greater than -1 and less than 1. Okay.